When faced with a circuit that looks like this, where there's a sinusoidal input and resistors and capacitors, I gave you a formula that will let you figure out what this circuit does. A formula, series of steps, right? These series of steps really fall under this sort of sinusoidal steady state analysis, but if you don't like that term, it doesn't matter. I'm just going to give you a series of steps. And if the capacitor was here, or if there was two capacitors, we'll see, it doesn't matter. These are the universal steps. The first step is replace capacitor C with 1 over JWC. And the second step is to treat this, as a resistor. And these two steps effectively remove the capacitors from the system. I mean, they're there, but they're not. They're there as resistors. So let's go through that step for this circuit right here. Well, step one is, and I think it's useful if you want to literally, you cross this out, and you write 1 over JWC. And if it helps, put a box around this to remind you that now this is a resistor, and this resistor has the value 1 over JWC. J is the square root of -1. C is whatever number was here to begin with, 7. So 7 goes here. And W is this W. So this is not an amorphous value. This is 1 over JWC. It's a number, right? But you'll notice it's an imaginary number because there's a J here, right? But this is the resistance. For our purposes of this resistor, it is an imaginary resistance. But okay, this is 7, and this is 1 over J3. Right, we just talked, okay, we're good with complex numbers now because we just went over complex numbers, right? So we have a 13 and a 1 over J7, right? But we're going to move ahead now and write the equation for the output. So what we're going to say now is that V out, and we're going to use the same voltage divider equation. How do we do a voltage divider? It's this resistance over the combination of the resistances. This is a resistance now. So we're just going to write 1 over JWC over 1 over JWC plus R, and this is multiplied by V in. This thing here is the transfer function. Why is it the transfer function? Because I said that's the transfer function, okay? I said that if you take the input and you multiply it by something and you get the output, that's the transfer function. Here's something, you're multiplying by the input, you're getting the output, it's the transfer function because I said it's the transfer function. But if you look, wow, we're really close to the story here, right? I said this is the missing piece here, right? I said all we need is C. And C is related to the transfer function. And so here we have this term, right? Sometimes people will refer to the transfer function as like, you'll see like H of JW. Don't worry about that. That just means transfer function, right? And this JW is only here because JWs end up appearing here, right? But I want to flag that up. You may see that in a circuits book. Transfer function. Okay. If the assignment was, the homework, please give me the transfer function of the circuit, you are now done. All right. But if the assignment is to tell me what the output is, you're a little bit stuck. I mean, you could substitute this in for here, right? So we could write instead of Vn, we can write A cosine of Wt. But I need the output like this. And to be clear, this is a real number. All right? I need a number here, 7, 6, 3. It turns out it's not useful if you give it to me in terms of j's. I don't know what to do with that. I really don't, right? And so what we need to do, and so I'm going to show you what we do in this case, okay? In order to take this and essentially convert it into C, right? We have a complex number here, right? And I want to convert it into a single number called C. Single number called C. It's the same C, all right? Let me show you how it unfolds, and then it'll become clear, okay, what the process is. At this point, we need to do a little bit of mathematical manipulation, but it's going to be all algebra. Remember, I told you it's all algebra, right? And so that's the win of this approach, that it only relies on algebra, right? That the really great mathematicians who figured out how to do this did it because they only wanted to do algebra. And so now we get to benefit from their hard work, all right, about what they're doing here. So I'm going to manipulate this so that we can see how. So the first thing I want to do is I want to, let's see, I'm going to multiply both the top and the bottom by JWC. If I multiply the top, so maybe I'll be, so I'm going to multiply this, to be clear, by JWC over JWC. Right, I'm taking this, and I'm allowed to do that because this is 1. Anything over itself is 1. So the top gets multiplied by JWC, making JWC over JWC, leaving just a 1. And on the bottom, I have JWC times 1 over JWC plus R, right? JWC times all that. And so that's going to equal 1 plus JWCR. I want you to think about, maybe I should have put it on one line, but I want you to be comfortable with this step. So we basically took the JWC, it's clear, right? If this had been 1 over Apple, the same thing would have happened, right? We would have multiplied by Apple, and we had Apple, right? So far, so good. We'll go through this again, all right? But this remains algebra. So now I'm left with this term. And what I would like to do is I want to go from A plus B times J to C. This is the step that I need to take. I need an A, I need a B, right? And that gives me the C, and guess what? I'm done. There's no more steps after that. Now you say, well, I have an A here, and I have the, like a J times something here, but it's on the wrong side. It's the 1 over. So it's not in the form A plus BJ. It's in terms of 1 over A plus BJ. So at this point, I need to do an additional manipulation. Keep on the same line. So what I'm going to do is I'm going to multiply this by 1 minus JWCR and also 1 minus JWCR. Right, this is this apple over apple, so I can multiply by this. It's a weird thing to do, but watch what happens. On the top, I'm just going to get 1 times this. It's going to be 1 minus JWCR. And what happens on the bottom? Well, this is A plus JB times A minus JB. It's this rule. This is complex conjugate, right? So what I know is all I need to do is square this term and square the next term and add them together. I mean, we could do it fully out, right? but hopefully you'll see that this is what happens. So all I need to do is square the first term, which is 1 squared, plus square the second term, which is WCR squared. That's why I showed you how to do the complex conjugate multiplication. Why? What does this buy us? Because now watch, right? Like whatever it is, like Moses separating the waters, I can now separate out the real and the complex. Because this can be rewritten as, and you can almost, I think you can almost see it without me rewriting it, as 1 over 1 plus WCR squared plus J times negative WCR over 1 plus WCR squared, if I did that right. Right, I could have put the minus here, but I wanted to make it very clear, right, that we have, this is A, B, J. I went from here to here. And there was a little bit of mathematical trickery along the way, right? But I needed to do it because I needed to get it into this form, right? Once I have it in this form, this is this, right? I can now take the A plus BJ and convert it and extract the C quantity, right? So let's do it. So C is going to be equal to the square root of 1 over 1 plus WCR squared, and then this quantity will be squared, plus negative WCR over 1 plus, again, WCR squared, and this whole quantity squared. All right? I know that there's a lot of terms in here, right? You could say, well, W, C, and R are all 1. We could have started with specific values, right? And then this would have collapsed into something, but I'm not collapsing it just yet. We can go through another example where we use specific values, right? So, but even though there's a lot going on here, I just want you to realize something. I'm going to put a dot over all the numbers. Number, no, not with this one. Let's see if pink gives us something. Yes, number, 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 number. They're just numbers. This is a number. You know, you put 1, 3, 6, 1, 3, 6, 1, 3, 6. And then you crunch it, and the number comes out. So we're done. We have the number. Right? We have the number. This is a number. And this number here is the C that we're going to insert here. But we can make this a little prettier. Prettier, you know. Let's see what this would look like if I were to try to combine these terms, right? So do 1 squared, and then here I would have WCR squared, right? That's going to be at the top. And then, because the denominator is the same here, right? So I'm ready to combine the denominator, right? Or I could do the denominator first. Well, let's do the denominator first. The denominator is going to be 1 plus WCR squared squared, right? That's going to pop it on both ends. this, when I square this, I'm going to square the top and I'm going to square the bottom, right? If this is a over b, what's going to come out is a squared over b squared. The question is, why did we separate them if we're going to put them back together again? Well, here we separated them, and there's this finicky j. And in this step, the key thing is that we've gotten rid of the j. Because guess what? We actually don't like the j. I don't like square root of -1, and neither should you, okay? It's imaginary. I forced it upon you at this point, right? Because it let us then do Ohm's law. But as soon as we're done, as soon as we've used it for what it's good for, we're trying to get rid of it. And so we've forced it on you, and now we're getting rid of it. And you could say, well, could we have done it some other way without that? Sure. We could have written a differential equation. But we're trying to stick to algebra. And for all the complexity you're seeing here, we are multiplying and adding. So they may seem like there's a lot going on here, but we're multiplying and adding numbers. Now let's look what happens to the top. It's going to be 1 squared, so I'm just going to write that as 1, plus, and then this is going to be squared, WCR squared. Okay. Now you'll notice something here. I have some element here, right? And I have another element here. It's the same element, right? Apple and apple, right? Apple over apple squared. I lose, right? Or you get it. A over a squared is just 1 over a. Right? I could have written this as this times itself and then canceled out one of them, right? And so I get C is equal to the square root of 1 over 1 plus WCR squared. Because this happened to cancel that out. Didn't just happen to. This will always happen as you see these things. And what I'm going to do is I'm going to rewrite this as 1 over the square root of 1 plus WCR squared. I could have stopped here. Actually, I could have stopped here, right? I could have stopped here because this was already a number, right? If this is 3, then it's still 3, right? But this and this and this are all the same, and by simplifying it, now I can write V out is equal to 1 over the square root of 1 plus WCR squared times A cosine of WT. And this is the answer. It may look ugly to you, but I want you to remember this is just a number. This is just the C. That's just the gain. And that's the only thing we need to figure out is the C. Now, I know what I just went through is a lot. Remember when I first thought it was a lot. We're going to go through it a few more times until it stops being a lot. What I'm going to tell you, though, is as we go through it a few more times, the mechanics aren't going to change. And so you're just going to see applying the same mechanics again and again. And so you'll get used to these mechanics, right, which are peculiar if you haven't seen them before. This, but at a high level, that's what I want you, this is the input. This is the circuit, and this is the output. This is the sugar and flour. This is the oven, and this is the cookies. And now that we can treat that as a multiplication, it's really interesting. The input lives here. This here is the circuit. There's nothing here about the input. There's nothing here about the output. This thing here is the circuit. This is the equation of the circuit. The transfer function is the equation of the circuit. The transfer function is the equation of the circuit. We have taken a physical object and converted it into a number. I mean, we were doing that. Let's go right back to voltage divider really quick. RB, RA, V, use different notation, V1, right? V2 is equal to V1 times RB over RB plus RA. What have we done here? This is the circuit. This is the circuit. A physical object full of all these elements has been collapsed, in this case to a number, but it's an equation. Input, circuit, output. When you look at it here, it's one of those things that's so obvious that the more I talk about it, it seems more confusing. Right? I mean, whatever. Thank you. I already knew how to do a voltage divider. I don't need this complicated like systems level analysis with V in and transfer function output. Right? But it isn't so useless when I go here. And I show you here again, input, circuit, output. And this represents the circuit. And in fact, everything we're doing is trying to reduce the circuit to a single number. Right? So now I want to go through it again. Right? That's it. There's no more. I'm just going to go through a couple examples until you get really comfortable with it. To be clear, if I'd put numbers, let's do numbers. C was equal to 1 farad. R was equal to 0.5 ohms. And the frequency was equal to 1. I like to give myself simple numbers, right? So let's say this was the actual situation. So what does that mean? It means that, oh, and the input, well, I'll give you an input too. And A is equal to 10. So what that means is that V in as a function of time is equal to 10 cosine of 1t. And obviously we have a, we have a resistance and we have a capacitance here. So then what is V out? Well, V out is given by this equation here. We kind of figured it all out. So it's going to be 1 over the square root of 1 plus, and then we have to multiply. Frequency is 1. Capacitance also 1. Resistance, is 0.5. All right, we're going to square that. And all this times V in. So all this times 10 cosine of t. So whatever this comes out to be. All right, that's how you, if you were given specific numbers, and you can see we have what we need. I mean, this is just a number, whatever this comes out to be, right? Whatever it comes out to be, maybe around 2/3. You're going to be multiplying this by that number, and we're done. So that's how you do it with actual numbers. Okay. Here's another one. A little different because I swapped the capacitor and the resistor. think maybe it's a little intimidating. There's sinusoids. How would you solve the circuit? Well, one of the first things you'd realize is that this satisfies the approach I described to you before, where you have a sinusoidal input, you have resistors and capacitors, and therefore you can follow the two rules, right? So let's follow the two rules. The first rule says that wherever you see a capacitor, cross it out and replace it with 1 over JWC, right? And you can think of this as now a resistor. All right. The second rule says to now pretend like that this is a resistor with this value. So this is now a resistor with this odd value. Okay, well, this is a voltage divider, right? So we can go in one step to V out is equal to V in times this resistance over the sum of the resistances. So that's going to be R over R plus 1 over JWC. It's not exactly this equation, if you look at it, right? It's not exactly this equation because it's a different circuit. Because it's a different circuit, it has a different equation. And this is the transfer function. Which I've also called the equation of the circuit. This fully captures the circuit. We have an input, we have an equation for the circuit, and we have an output. And because we can multiply this by that, this is called the transfer function. And if the assignment was to give me the transfer function, you are now done. You are now done. But again, this J is pesky because it doesn't really allow us to, because we know that the output is going to have the form B cosine of WT. And this needs to be a real number. And so we need to remove the J. Having inserted the J, we now need to remove the J. Okay? The way we remove the J is very similar to what we did before. Let's manipulate this a little bit. So first I'm going to multiply top, and I'm going to do this in one step. I'm going to multiply both top and bottom by JWC. I'll write it. R times JWC over R plus 1 over JWC times JWC, right? I multiplied both top and bottom by JWC. And if you want to know why I'm doing this, I'm trying to get it into this A plus BJ form. Okay, that's really what I'm doing. And I'll show you how to do it. So I did that just for simplification. And so now I get JWCR over JWCR plus 1. You see this WCR? Do you see how it's like the resistor and the capacitor somehow found each other? Plus this W, right? It's not a coincidence. It always happens, right? It's like two people and they're good friends and they're at the party. They always go to find each other. When you're solving these, you'll be surprised how the R's and the C's will always find each other. And they'll be bound by this W. This remains not in the form A plus BJ, which I need, right? Because I need to get to this. I need to apply this term here. Okay. And it's not in this term because the J is in the, as long as I have a J in the denominator, it's not going to be in the right term. So how do I get rid of it? The same way I did last time. I'm going to multiply this by 1 minus JWCR, and the top is also going to be multiplied by 1 JWCR. And I'm doing this specifically to get rid of the complex number in the denominator. Let's see what happens. the top becomes, well, we have J, W, C, R. And then we need to multiply this by itself. So we have a negative, but the J times the J is another negative. So in fact, we end up with plus WCR squared. All right? So this times this, it's like JA times minus JA. You actually get A squared. Because even though you think you would start with a minus, the J's, right? Cancel that. So that's that J times J function there. And that's where you get a positive here. All right? Actually, I don't think it'll end up mattering in the end, but this is positive. All right? On the bottom, it seems complicated, but remember there's this complex conjugate rule that says we're just going to end up with A squared plus B squared. Right? So what's so 1, right? The A squared is 1. I can write 1 squared. And then the B is WCR, right? 1 plus JB. This is the B. Going through this a little bit faster than I did before, but see if you're following. So this is WCR squared, right? A squared plus B squared with the A and the B, right? I mean, you got your notes, you can go through it. And now what would happen is that I have a, you can see here, I have my imaginary component and I have my real component. I've actually, at this point I have A plus BJ. Let's write it out. Let's write it out. So the A is going to be WCR squared over 1 plus WCR squared plus, and the J times, right, times WCR, hopefully I did that right, over 1 plus WCR, oh, this whole thing is squared. WCR squared. Okay. That is A plus B times J. And again, if you feel like there's a lot of terms here, just remember you can put 1, 3, and 7 into all these things, and it'll become 13 plus J 16 or something else, right? This is just a complex number. And therefore, and now in the final step I told you, in order to get this C, I need to combine these into this term here. So let's go ahead and do that. And once we do that, things will actually start to get simpler. So let's do that. Here. All right. So I'm going to have C is equal to a big square root. And I'm going to take A and square it. So it's going to be parentheses WCR squared over 1 plus WCR squared plus the B term, which is just WCR over 1 plus WCR squared, and all of this is squared. And that is the C term. And there may be a lot of terms here, but again, just numbers. If this is 3 and this is 7 and this is 6, you're done. Just crunch it through and you have your C, and the C is the only thing we needed. Okay, the C is the only thing we needed. However, right, let's massage it a little bit, see what it looks like. I want to combine the top and the bottom, so I'm going to have C is equal to the square root of, and let's see what we get here. So this is, I'll write it out, WCR squared and then this term here is squared plus WCR squared over 1 plus WCR squared, all this is squared. But there is a simplification here. Where do I put it? I'll squeeze it here under it maybe and see how much we can get in this space here. Where I'm going to rewrite this, it's going to be a little tight. Should I do it here? I'll try to put it here. This is equal to WCR squared times 1 plus WCR squared over 1 plus WCR squared squared. This is like, did I do that right? Yes, yes. WCR squared times 1 will be this term, right? And WCR squared times WCR squared is this term here. I went from here, I pulled out the WCR squared, right? Almost as if, just think of WCR squared as like that was apple. So if I had, or A squared, plus A, right? And so that, and the reason I did this was for a very specific reason. You will now notice that I have a term here, 1 plus WCR squared, and I have here a term on the bottom. I know it's written a little sloppily, but if there's a 1 WCR squared, it's like I had last time, right? It's like having A over A squared. Well, that's like 1 over A, right? Or apple over apple squared. And that's why I did it. And sorry if it's a little messy, but then we will go here. And we will be able to write that C is equal to the square root of WCR squared over 1 plus WCR squared. And C is therefore equal to WCR over square root of 1 plus WCR squared. This and this are the same. Okay, they're the same, but you can notice there's a lot of simplification. And you'll notice that there's a lot of simplification that happened here as well, right? And so now we're done. And we can go back here. And we can write that V out, right, is equal to, this has now been converted to this form, right? I converted this transfer function into its C form, right? It's been transformed, so that's going to be WCR over square root of 1 plus WCR squared times the input, which is A cosine of WT. All right. It's like what we did before, right? And we just went through it again. Now, in this case, this is the result. And in this case, this is the result. And they're different, right? Because it's a different circuit. Let's take a moment and imagine what this result, well, let's imagine what this result would give us. I want to consider two situations. Situation A is when the frequency is large. So it's a fast sinusoid. It's wiggling very, very quickly up and down. As you can imagine, situation B is when the frequency is very small, so that is a slow sinusoid. So I want to consider these two situations for both these circuits. We can plug in actual numbers, but let's try to do it just thinking about big and small. Let's start with this circuit here. So in the first situation, situation A, well, it's a big W, right? That means that this number is very big. Right? This W is a big number, a billion. So I have 1 over the square root of 1 plus a billion times C times R squared. This is a very small number. So in situation A, V out is approximately equal to 0. You say, well, what do you mean 0? Doesn't it depend on the input and other things? Maybe not. If this is a high-frequency sinusoid, right, because this term here has W in the bottom, the sinusoid will not make it through. It's not coming out the other end. Nothing's coming out the other end. A sinusoid comes in, and it's going to get eaten up. V out is 0. However, let's look at situation B. In situation B, we have a very slow sinusoid, which means that W is a very small number, like 0.000001. Okay. So we have 0.00001 times some numbers squared. This is a tiny number. It's nothing. 1 plus tiny is 1. Right? If this is tiny, then multiplying it by C and R is still tiny, squaring it even more tiny. 1 plus a tiny number is basically 1. And the square root of 1 is 1. And 1 over 1 is 1. And so what we get in this case is that V out is equal to A cosine of WT. So when the frequency was big, nothing came out. And when the frequency was slow, the thing that came out is the same as the thing that came in. This circuit seems to say, I'm looking at what's arriving. And if what is arriving is a very high frequency, I'm not going to let it through. That's what I do. And if what is arriving is a very slow frequency, I'm just going to let it through, clean, untouched. High frequency, blocked. Low frequency, through. There's a name for this. There's a name for something that where did I put it? So we're talking now about this circuit here. Okay. There's a name for a circuit that, to be clear, right, blocks high frequency and passes low frequency. What we previously talked about is this and this. A high block, low pass, so it's just going to be called a low pass. This circuit is referred to a low pass, or specifically a low pass filter. Low pass means that low frequencies pass and high frequencies do not pass. And that is a consequence of this W sitting here that we derived, right? Remember, this is this, right? So what we have now is a circuit that when a high frequency arrives, this goes to 0. And therefore, the high frequency does not show up on the other end because it's multiplied by 0. When a low frequency shows up, this circuit basically says, go right on through. Its C becomes 1, right? A C of 1 means pass because you're just multiplying everything by 1. So this is why this is called a low pass. And we did this for extreme examples. Later on, we'll talk about the full spectrum of frequencies, right? Now let's look at this one, and you think, and maybe you'll see what's going to happen here. Let's condition A. In A, W is some big number, like a billion, right? A billion. All right, so that's a billion. What happens here? Let's say this is a big number, like a billion, right? So okay, billion times billion, all right? And obviously when I square it, it's going to be even a bigger number. When I add 1 to a billion squared, the 1 doesn't add anything. This 1 doesn't matter. This is the player. This is to be ignored. So this is really the square root of WCR squared. But that's just WCR over WCR. And that's just 1. So in this case, when W is really big, this term converges to 1. The C, so to speak, right? This is the C. This is the C. So that means that in this case, the output, V out, is just going to be A cosine of WT. See, in this case, when the W is really big, this becomes 1. And when this becomes 1, well, then nothing happens. It just goes right on through. How about condition number 2? Where the frequency is a low number, like 0.00001. Or let's think of even 0, right? In this case, we can think of just pure 0. Well, or about 0. Well, about 0 times a number, it's going to be a very small number, right? All right. What happens here? Some small number, let's say 0.01 squared, but we have the 1 here, right? So it's 1 plus 0.01 squared, like 1. Square root is 1. 0, a very small number over 1 is a very small number, and so what we get in this case is that V out is 0. Let me go through that again, if it's not clear. This is a tiny number, because in this case, W is small. And this is a tiny number. Okay. Tiny number squared is tiny. 1 plus a tiny number is 1. Square root of 1 is 1. Tiny number over 1 is 0. So what does this circuit do? Well, it passes the first case, right? It passes the fast frequency and it blocks the low frequency. And so we will call it a high pass. Because high frequencies are passed, whereas in this case, low frequencies are passed. We have a circuit here. We consider two ways to build the circuit. In both cases, we use one resistor and one capacitor. In both cases, we make a voltage divider. In one case, we said, let's build a voltage divider and put the capacitor on the sort of the output side and the resistor here. In the other case, we said, let's put the capacitor here and the resistor here. Right? Those are the two things we put in this box. Right? And when we did that, we built a low-pass filter and a high-pass filter. A low-pass filter is something that high blocks, right? When high frequencies come through, they don't show up on the other end, but a low does. It's like a filter. However, if we built this version, the exact opposite would happen. This would be a high-pass, low block. And I didn't tell you that. We derived it. We derived it by looking at what is the, this is the equation for the circuit. The equation for the circuit has a W in it, right? And that's where this behavior comes in. The equation for this circuit has a W in it. Once again, the voltage divider. Call it RA this time, RB, VN, V out. V out is equal to RA over RA plus RB times VN. There's no W here. That's the difference. We never noticed it before because we didn't care, right? But the this term here, which is the C, which is the transfer function, right, doesn't have a W in it. That's why this thing didn't really care about frequency. It never came up. Because if you put a resistor in a resistor, frequency doesn't really matter. It doesn't show up in the gain term. But as soon as we added a capacitor, W did show up. Right? Now, you could say, well, I'm just curious. I don't know if that's is this in the A plus BJ form? Right? Well, it is. A is this, and B is 0. I mean, you could say, we can look at here, and you could say C is equal to the square root of A squared plus B squared. C is equal to the square root of RA over RA plus RB squared plus 0 squared. I mean, it's just going to pop right out, right? Yes?
How large or small does something have to be considered, like, how fast?
Okay, so the question is, how large or how fast or slow does something have to be? And that is an excellent question, because what I have done now is I've dodged that bullet. I've used extreme examples. I've said very fast, very slow. Okay. Is 10 hertz fast? I don't know, maybe kind of. Is 100 hertz fast? Could be. Could be. Is 101 hertz? So there is something lacking here where, while it's true, I think you would agree that if the frequency was a billion trillion, you know what I mean, we're safely in the high, but what about 101 hertz? Let's plot this. Let's plot this. I'm going to say here that this is C. C is this quantity, right? And I'm going to plot it versus frequency. So tick, 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 tick. I want you first to notice that this can only go between 0 and 1. there's no way this can be above either. I mean, these were the extremes, and there's no way to break outside of those extremes. It's also a little bit consistent with, remember we talked about voltage dividers? They can divide but never give you, voltage dividers never give you more than what you put in. It's the same thing here, right? I mean, voltage divider, what does C go between? 0 and 1. So it respects the principle of the voltage divider. And so I can start from 0, and I can end up at 1. And we've discussed that in this case, for the first case, which was very, very high frequency? High pass, yeah. We're going to be here. And for very low frequency, we're going to be here. And if you were to plot this out, you would see a behavior that look like this. So this would be very high. And Adrian, you're good to be dissatisfied with what I mean by that. Very low. And then there's some situation here that this doesn't jump instantaneously. There's a transition. I'm going to pick a frequency. All right, I'm going to pick a frequency. I'm going to say, what if the frequency was at 1 over RC? Say, what? What do you mean by 1 over RC? Right? I mean, for example, if the resistance was 1 and the capacitance was 10, then the frequency happened to be 0.1. Or if the resistance was 0.1 and the capacitance was also 0.1, then the frequency, the radial frequency, happens to be 100. Do that? Okay. You say, well, why did it work out that way? Because I said it did, right? I'm just saying that's what happened, right? In one case, you had this resistor and that capacitor, and this frequency showed up. In that case, this and that. And I'm saying, well, more abstractly, what if the frequency that showed up, right, happened to be, right, at 1 over R, whatever the RCs were. So if the R and the C were 1, right, just imagine, okay, I want to consider that abstract situation. Because, why did I do it that way? Well, let's plug that into this equation. Right, let's plug that in. So we have, let's think about it. 1 over RC times RC over, and then we have 1 plus 1 over RC times RC. Remember how I said the RCs always get married? And so by doing that, I can rewrite this as V out is equal to, this is going to become 1 over, this is also going to become 1, right? 1 over CR times CR is 1. 1 squared is still 1. And end up with 1 plus 1, and end up with the square root of 2 times Vn. What am I saying here? I'm saying that if it just so happened that the frequency was 1 over RC, that's this point right here. If it just so happened, right, then this would be the value of C, right? This would be the value of C, right? And this is, well, what is this? It's not 1, right? It's not 0. It's like a middle number, right? It's the middle, right? It's somewhere in the middle. Specifically, someone do this on your calculator. What is it? Square root of 2 is 0.6. What does it come out to be? 0.7. All right. So right here, I should have put it with this one here. The value is 0.7. And this thing here has a name. We'll put a lowercase c, and we'll cut it the cutoff frequency. Now, what does that mean? If the frequency is a lot bigger than the cutoff, you're here. All right, so let me write it out. This is frequencies greater than the cutoff. And here, of course, is frequency less than the cutoff. So if the frequency is less than the cutoff, you're here. If the frequency is greater than the cutoff, you're here. And if it's not like a lot bigger and it's not a lot smaller, then you're kind of here, which we don't like to be in. Because it's like, well, what does that mean? So for example, in this case, if I'd built a circuit with a resistance of 1 ohm and a capacitance of 10 farads, the cutoff would have been 0.1. That means this value is 0.1. And now I can tell you what big and small is. In this case, 10 is big. And 0.01 is small. If I'd built a circuit with a resistance of 0.1 ohm and a capacitance of 0.1 farad, then this cutoff, right? So in this case, in this case, the W cutoff is 1 over RC, and that's equal to 100. Right? Yes?
We saw a similar graph with comparators, but then we said that the increase is so steep that it's practically just like one place would be.
Yes, we did something similar with comparators, and in that case, this was so steep that it didn't exist. In this case, there is a range to work with. It is possible. So if you built a circuit with a resistance of 0.1 and a capacitance of 0.1 farad, the cutoff is 100 hertz. Or this is really radio frequency, but 100 frequency, okay? So that means that in this case, if a 10 hertz would show up, it's actually on the low end. And it's on the high end. And 1,000 hertz, I'm sorry, would be on the high end. Don't know if I'm making this clear. When you build this, you pick the resistance and capacitance. You pick it. You could pick this. You could pick this. Right? So if you picked this, and you picked this, and you both built this circuit, you didn't make the same circuit. You could say, oh, but we both have a voltage divider with a capacitor here and a resistor here, but you didn't exactly make the same circuit. Because if you were to draw in absolute terms, frequency versus gain, and this goes from 0 to 1, in one circuit, it could look like this, and in another circuit, in another color, it might look like that. These are both high passes because they like the highs, they favor the highs, and they don't like the lows. But they have different cutoffs. This is one cutoff, and this is another cutoff. Two different cutoffs. And that is given to us by this equation. Let's reverse the problem. I want you to design a circuit that allows 1,000 hertz to pass. And by that we mean that it has a gain of 1, but does not allow 100 hertz to pass. And by that we mean a gain of 0. Okay. Second, right? A circuits problem. I want you to build me something. Build it. And once it's on the table, I want it to have this behavior that if a 1,000 hertz sinusoid shows up, right? I'm being wishy-washy with its radial or absolute frequency, but 1,000 hertz shows up, it gets through. But if a 100 hertz shows up, which is still pretty fast, but not as fast, it doesn't get through. You need to design the circuit. Okay, so you're thinking about it. All right, so 1,000 hertz pass, 100 hertz doesn't pass. It kind of sounds like a high pass, low block. I need to build something that passes high and blocks low. It's certainly not going to be a voltage divider because a voltage divider isn't picky about frequencies. Everything passes equally, right? So you know right away that you need to build this circuit. So you say, okay, here's my Vn. And I'm going to take a capacitor. I'm going to take a resistor. I'm going to call this one my R1. I'll call this my C1, so it's a little messy. And the V out is therefore measured here. Right? And that should do it, except you're not quite done because your lab partner's like, well, I have a lot of resistors here. Which one do you want me to give you? You can't say, oh, any one, just give me any one. You have to pick your resistance and you have to pick your capacitance. How would you pick it? I think what you should do is I think you should look at this picture here. Right? There's a lot of increments here, right? A lot of increments. What this picture tells you, this is the picture of the circuit. And that's a big idea. So this circuit here, which is a physical object, is represented by this equation. And this equation is this plot. This plot is this circuit, and this circuit is this plot. So I'm thinking about the circuit, but like it's really, I don't know, I can't look at this. I don't know, it's really very hard to know what to do here. Right? I don't know what resistance and capacitance to pick looking at the circuit. I don't know how you would know that. But if I look at this picture here, I can say, well, I'll tell you what. I know that it's going to have this kind of this is C as a function of frequency, right? And I know that I want 1,000 hertz to be here on this side. And I want 100 hertz to be here. Right? I know that, right? I want 100 hertz to be in, some of these people will call this the block band and the pass band, right? But I know that I want 100 hertz to be like on this end, right? And so that means that this thing here needs to be between these frequencies. If the cutoff, and we're just going to come up with an example, was 500 hertz, then I would be sitting pretty. Because if this is 500 hertz, then 1,000 hertz is on the good side that gets through, and 100 hertz is on the bad side. So I want this picture, but I want this picture where this here is at a 500 hertz. Right? And we're talking about radial frequency, and therefore I'm going to say I want 1 over RC to be 500. If I pick a resistance and a capacitance such that 1 over the resistance times the capacitance equals 500, I will create this circuit. You can say, but there's different combinations, right? I mean, this could be this could be whatever. This could be 0.1 and whatever it is, 0.05. There's different combinations, right? You can say, well, which ones? Up to you. You're saying, well, doesn't it matter exactly? No, it doesn't matter exactly. It's only the relative that matters. Okay? So if you happen to have not a lot of capacitors, like you only have 1 microfarad capacitors, that's great. Just find the associated resistor. This is a big idea. Let's go through it again for this one. I want to plot this function, just like I did for the other one. So what I'm going to say is that I have a frequency here, and it's increasing in this direction. I'll try to do it neater this time. And I have a C, this all-important C, right? Which is what the gain is, what happens to the input. The C in this case can only go from 0 to 1. And the reason is as this function only goes from 0 to 1. It can be as big as 1, but no bigger, and it can get as small as 0, but it can't go negative, and it can't go greater than 1. And the general behavior, if you were to plot this, would be something like this. Where here I have low frequencies, and here I have high frequencies. All right, this would be my range. And so if a very high frequency arrives, this doesn't go up, it just stays down. If a very high frequency arrives, C is 0. That means it doesn't really get through. If a very low frequency arrives, C is 1. So it does get through. But to Adrian's point, what's low and what's high? If we imagine that I pick a frequency that happens to be at 1 over RC, whatever that is, what would happen to this equation? Well, W is 1 over RC, right? So 1 over RC times CR, I'm just canceling it out. So this becomes 1. 1 squared, still 1. 1 plus 1 is 2. 1 over square root of 2. So in this case, the C becomes 1 over the square root of 2. And now you're saying, this is like so familiar. It sounds almost like exactly what we did here, right? I picked that same frequency, and I also got 1 over square root of 2, right? This class is full of repetitions, full of repetitions. I told you that the R's and the C's always get married together. And that's why when we pick a frequency that is 1 over RC, we always start to do this sort of like intermediate collapse. And so what I can tell you now is that at a frequency here, W cutoff, the associated gain is about, like we said, 0.7. So when I say high, I mean greater than WC. And when I say low, I mean less than WC. Same discussion we had here. And so I changed the assignment. All right. I deleted what was here. Block. Okay. Okay, think about this one for 4 minutes. I mean, I can give you more time, but maybe some of you have a theory. So first up, would you build this circuit or no? You want a circuit that blocks highs and allows lows, right? So you do that one. So you'd say this is not the right circuit. Oh, I didn't have to erase it all, but you would build that. It's not too complicated. You would simply need one resistor and one capacitor. All right, this is the general, but you still got to pick the resistance and the capacitance. Right? You have to pick the right resistance and the right capacitance. Specifically, you would like 1,000 hertz to be on this side, right? And 100 hertz to be on this side of the line. So which resistors and capacitors might you use? I mean, I didn't make it complicated. What might you use? Yeah. A capacitor of 0.1 microfarad and a resistance of 22 kilo ohms. Because what cutoff does that give you? 454. 454 hertz. Or radio frequency, but we're being vague about that. And so by choosing this capacitor and this resistor, the 1 over RC, which means where this thing lands, is right here. Okay? And so that's it. You just did a you just did a filter design problem. Right? And the last thing I want to tell you is to do what I think that to solve this problem, you weren't smart enough to look at this and say 0.1 microfarad, 22. You can't look at this and do it, but you can look at this and do it. So by going from here to here to here, I didn't just show you how to solve problems that look like this. I've actually also showed you how to do design problems. When we design filters and other things with capacitors, we live in this domain. All right? And I'll give you, and in this axis, right, is frequency. So fancy word people will sometimes use is frequency domain. This is a frequency domain representation of the circuit because frequency is plotted in the x-axis. Right? So that's frequency. That's why people use frequency domain. You could say transfer function, frequency domain. I remember the transfer function is h of jw because there's a w there. But for the approach that I've sort of shown you here, it's good enough for now to just remember that it's just this C. And it's the same C that happens to come out of complex number, right, addition. All right?